Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2023 chemistry exam multiple choice section, part 1 of the Northern Hemisphere. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And you guys, let's smash through this video. Alright, question 1. Which of the following is an equation for the combustion of a fuel? Now, when they say combustion, it's another word for oxidation. So if you get an exam question that says, write the oxidation reaction for a fuel, it's the combustion reaction. So oxidation and combustion are basically the same. That's what, basically they are. So let's have a look at these. Now, we know combustion reactions have a negative enthalpy change. So which of these are they? Well, of course, it can be C and A because we can see that the enthalpy change is positive. So now it can only be B and C. Like we said, combustion, it's another word for oxidation. And basically for combustion to occur, you need oxygen gas. You need an oxygen gas. So having a look at this, you can see that this one has oxygen gas and we are forming CO2, which is, great. This one over here, we are forming CO2 and H2O, but, that will confuse some students because they'll be like, wait, isn't H2O and CO2 a products of combustion reaction? True, but is there, oxygen reacting? That's what really, that kind of defines what combustion reactions for a fuel is because it's the oxidation of a fuel. So it's the fuel reacting with oxygen. So it has to be this one here. You can see that's reacting with oxygen. Beautiful, so choose B. Question 2. Which of the following is true about secondary cells? Remember, secondary cells are able to act as galvanic cells and electrolytic cells. Side reactions do not occur. Rubbish. Side reactions do occur. And that's why your batteries, like for example, your batteries, let's say for your phone charger, are actual secondary cells because they can recharge and discharge. Now, when you're basically put them in like a hot temperature room, let's say you go on a beach and you have your phone, you're gonna you're basically increasing the rate of reaction of side reactions. And basically this is what kind of destroys and deteriorates the battery life. And so, side reactions do occur for secondary cells. Of course they do occur. Fuel cells are a type of secondary cells. Wrong. Fuel cells are not primary, my apologies. Basically, fuel cells are galvanic cells. Like galvanic, not actual electrolytic cells. So be careful with the wording here. Secondary cells are both electrolytic and galvanic, but we know fuel cells are basically just galvanic. C. The cathodes are always positively charged. Rubbish. It depends. If it's acting as a galvanic cell, yes, the cathode is positive. But if it's, acting as an electrolytic cell, it will be negative. D. Electrical energy is transformed into a chemical. Yes, it can. Or it could be vice versa. Chemical energy goes for electrical. So D would be the best here. Question 3. Consider the following concentration versus time graph. Okay. Which of the following reactions could produce the graph shown above? Alright, let's have a look at this. Now, what I can see is the ratios at which they are decreasing. Like, for example, this is where it starts for this graph, and this is where it ends. Draw a nice straight line. So this is like the distance, basically. Let me draw a nice. This is like the distance. This is the distance, and I consider that as 1. Well, let's have a look at this one over here. So you can see that this one also decreases by the same distance. There it is. 1. So they basically have the same length, so distance. So basically, they decrease by 1 mole each. Whereas this one over here increases double. You can see that. It starts over here, and it basically ends. So it's actually double those two. Meaning that basically, there's going to be like the coefficient basically for two of them they're going to have two the coefficients are going to be 1, whereas one of them is going to actually have a 2 in its coefficients. Let's have a look at A. A is wrong because you can see, remember, there are 3 so we can see that there has to be 3 species. Of course, because you got this one decreasing, this one increasing, and this one decreasing. There has to be 3 species. This one has only 2. B, hydrogen gas, iodine gas, and gives us this. Now, this is true because you can see, like we said, one's going to have 1 mole. The other one we should also have another one that has 1 mole. And the other one should have 2 moles. This one actually looks good. Let's look at the next one. this one's wrong because you can see that one of them is 3 times the amount, and one of them's 2 times the amount, and the other one's 1 time the amount. And that's wrong because we know they're basically 2 of them have to be 1. D, same as always, you can see that this is also wrong because you're forming 2 that are doubling. We only know that's one's like, doubles in terms of moles, while the other ones are 1. So only B. Very nice and easy question. Question 4. Bioethanol is a fuel produced by. So easy. So is it the fermentation, aerobic digestion, transesterifications of fats, or a substitution reaction of ethene? Now, easy. Bioethanol is basically it's basically produced through fermentation. So basically the fermentation of glucose. So if you have glucose, which is C6H12, oxygen, and basically if you have bacteria that's acting as a catalyst, and it will basically decompose to CO2 and 2 ethanols, and these are your bioethanols. And these are what we want. These are your bioethanols. So yeah, this is a fermentation reaction. Anaerobic digestion, that actually creates biogas. Transesterifications of fat, that creates biodiesel. A substitution reaction of ethene, not true. When you have a substitution reaction, so let's say you have a ethene here. Now, what are we substituting? Are we substituting a water? A water? If you add a water, it's not bioethanol because you could where did that ethene come out? Where did this come out from? It could have came out from coal, which is then hence not bio anymore. It will actually just create ethanol itself. So that's not right. So it's only A, fermentation. Beautiful. Question 5. Which of the following is the percentage atom economy of the reaction that converts propene to propane? Easy. So propene is what? It's basically C3H6 because it's 3 times 2. Yep. That basically goes and it actually reacts with hydrogen gas, of course. Because if you react it with hydrogen gas, what's going to happen is basically those double bonds break, and hence it will become propane, which is basically a C3H8. If I'm not mistaken, is that right? Let's check. You got that, and that. So 1, 2, 3, 4, 5. Beautiful, that works. So remember the atom economy formula. It's the desired mole. So you know how we want to basically form this much? This is what we want to form, the propane. So what's the mole of it? The molar mass. So I'm going to write molar mass of C3H8 divided by the molar mass of your reactant. Now, the molar of adding these here, isn't it going to be basically the same? Because if you add those carbons and add these hydrogens, isn't it basically the same when you times it by 100? These are just going to cancel out to 1, so it's 100%. Let's choose D. Beautiful. Nice. Question 6. The reaction between sulfuric acid and sodium chloride to produce hydrogen gas is given below. All right. A beaker of H2SO4 was placed on a balance in a fume cupboard. NaCl was added to the beaker in the stoichiometric ratios shown in the equation. The following observations were made. The reading of the balance immediately decreased. Of course, it would decrease because if you react these two, you're going to be forming hydrogen gas, and the hydrogen gas will release. And so, yep, that's why. So the reading of the balance immediately decreased, but stabilized at a constant value after 10 seconds. The liquid level in the beaker increased when NaCl, so sodium chloride, was added, but no further change in the liquid level was observed. So the reaction has what? So fast rate of reaction or high extent reaction? Okay, so we're talking about, let's look at the rate of reaction. Remember, the rate of reaction is how quick the reaction basically goes. Now, have a look at the first dot point. It said, the reading of the balance immediately decreased, meaning that when we added these two, straight away, hydrochloric acid basically straight away released, meaning that it is an actual fast reaction rate. It has a very fast reaction rate. You can see that it says immediately decreased. The balance immediately decreased. So it means that straight away, we formed hydrochloric acid, which is great. So I'd say that it's a fast reaction, right? When we're talking about the extent of reaction actually, defines basically how much do those reactants basically form products. If they mostly became products, that is a high extent of reaction. If it's the opposite, if we still have a lot of reactants and not a lot of products, only little products that was formed, that's a low extent of reaction. So an extent of reaction can be actually in other words, your K value. That's what it really defines it. Now, looking at the dot point 2, it says the liquid level in the beaker increased when NaCl was added, but no further change in the liquid level. So that tells me it actually has a low extent of reaction, because if you think about it, the liquid level in the beaker increased. So we have a beaker here, and say you had basically this here was your H2SO4, your hydrochloric sulfuric acid. And so basically you put sodium chloride, and basically at the end the volume had increased. You can see that the volume had increased, meaning that we still have more, if these actually didn't react, of course they reacted, some of it would have reacted to create, the hydrochloric acid, but most of them are still in its reactive form. So basically the extent of reaction is slow. It means that all those reactants did actually just straight away form into our products. So that means, this tells us that we have a low extent reaction. So choose B. 7. A triglyceride is shown below. The number of carbon, so C double bonds in the triglycerides are what? All right, let's have a look at it. Okay, we can see that there has to be here C double bond, because you can see this part here. So it has to be like a, C double C, 1H, 1H, and then forms, So that's one double bond there. So that's, let's just consider that as one. What about here? Well, let's look at the pattern. We know it's going to end with a CH3. So look at that C19, H31. We know it's going to end with CH3. So if I minus that away from it, what would it leave me with? 28? Yep, it would leave me with 1828. Now, if this is the key. If it didn't have any double bonds, these would be the pattern. Basically the pattern, you can see it's a CH2, meaning that CnH2n. Meaning if you have one here, you get two hydrogens. That is the pattern. So if I do it here, so having a look at it here, this part here. So C18 should release me 36 hydrogen if it was a straight bond. Now this here is a big no-no, because you can see that it means we have double bonds, because it's not that. But how many double bonds? Now when a double bond basically forms, let's say you have a double bond that forms, we actually basically normally in this equation we lose two hydrogens, and that means that we have a double bond. So let's count with the hydrogens. So to make it equal to 28. Let's think. So it starts with 36 hydrogens. And so if I take 2, that's already one double bond. So that's 34. If I go to 32, that's 2 double bonds. 30, that's 3 double bonds. 28, and that's 4 double bonds. Now we've reached it. It means this here molecule has 4 double bonds. That is the structure. So we have basically, so 4 double bonds here. All right. And what about here? We only have 1 and then another 2. So overall, we have 1 here, 5, 6, 7. We have 7 double bonds. Beautiful. Not a bad question. Just, Question 8. A diagram of a galvanic cell at a standard condition is shown. So, okay, what do we have here? Some have relevant, reactions relevant to these galvanic cells are given in the table. All right. If the galvanic cell produces 1.5 volts, the anode and the cathode should be made from which of the following? So if we want to produce 1.5 volts, having a look at this, what do we do? These two, look at this. If I take this minus this, I should actually get 1.5 volts. So these are the ones that are going to be reacting. And remember, if your voltage is high, like for example, this one's the highest voltage, it means it's the strongest reducing one. In other words, it's the strongest oxidizing agent, sorry. So this is going to be reduced in this molecule here. Let me just highlight it. And whereas this one over here, because it's a lot, it's going to go for oxidation, and hence it will oxidize. Beautiful. Now, what should basically like the cathode and anode be? Well, let's have a look at the cathode where this is going to occur. Remember, this is because it's going for reduction. We can see it's an aqueous solution. Aqueous solution, of course, we don't have a solid form of it. So, of course, we use an inert electrode, which, for example, we have to use platinum in this case. So your cathode has to be platinum. So B and C are wrong. A and B are wrong. SN has to be platinum. For the other one, yeah, we can use SN solid. So beautiful. So choose D, SN solid for the anode. Nice. Question 9. A galvanic cell has the following setup. Half cell 1, it has acidified hydrogen peroxide, solution with, platinum electrodes. Nickel nitrate, so nickel basically has to have nickel ions. And a solution of nickel electrodes, so nickel solid. And we also have hydrogen peroxide. So let's look at which one. And it's acidified. So that's a key word. So H plus ions are going to be into it. Let's look at H2O2. So let's look at that hydrogen peroxide. This one looks good because you see you have also that H plus ion because it's acidified. Also, this one's good. This one looks good. We also have to have nickel solid, nickel 2 plus. And yeah, those are it. So let's have a look at, so what we want to find is when the cell is operating, the oxidizing agent is what? Remember, your oxidizing agent is the one that's been reduced. So it's going to be the strongest reduction one. So it's going to be on the left. It's going to be the left top one. So on the left, and the highest one, which is H2O2. Beautiful. So D. Nice, not too bad. That's D. Question 10. Which of the following statements is correct? Reducing agents help prevent oxidative rancidity. So remember, oxidative rancidity is that smell, that odor of fatty acids, like those fats and oils. So for example, when you what happens with oxidative rancidity is basically if you have a double bond like a fatty acid, basically it reacts with oxygen. And so when it reacts with oxygen, it forms ketones and aldehydes, basically that smell that comes from that. So, all right, reducing agent helps to prevent oxidative rancidity. So let's think about it. Reducing agent. Remember, reducing agent is the one that's going to be oxidized. Now, true. Actually, that makes sense because you got to remember that oxidative rancidity is when oxidation occurs. Like, basically, oxidative with that word is basically what's happening is the reaction is it's oxidizing. Basically, the reaction is oxidizing when oxygen reacts with the double bond, or it basically forms those ketones. It's actually oxidizing. Hence, if we're putting a reducing agent, remember your reducing agent is like an oxidation. It's like an extra oxidation, and if it replaces that triglyceride or that fat, it can actually decrease the prevent oxidative rancidity because it will be itself oxidized, like you go through oxidation, whereas the triglyceride or fats won't be. So that's actually, a reducing agent is one of the best ways to actually prevent it. So that looks good. All fatty acids undergo oxidative rancidity at the same rate. Rubbish. Some fatty acids that have double bonds basically go quicker because they are more susceptible to those oxidation reaction. So let's have a look at C. Temperature does not affect the rate of oxidative rancidity of fatty acids. Rubbish. High temperature does affect it. It actually increases the rate of reaction. It just basically, so rubbish. D. Antioxidants react with the carbon-to-carbon double bond in unsaturated fatty acids. No, antioxidants are basically, are free radicals. Basically, they don't actually react with that carbon-to-carbon double bonds. So, the only possible answer is A. Beautiful. 11. Consider the following statements. The half cells must be separated for the cell to operate. This cell requires reactants. The anode in this cell is always negative. Which of the following combinations of statements applies to the secondary cells and fuel cells? All right, easy. Now, straight away, one of the most easiest way is look at the anode in this cell is always negative. Remember, in secondary cells, it can switch, basically, because it depends on if it's acting as an electrolytic and galvanic cell. So it's not always negative. It can also be positive. So if you look at the secondary cells, if it has 3, it's wrong. So these are wrong because it has 3, both of them. Everyone looks the same except just this one has 1. Well, let's have a look at one. The half cells must be separated for the cells to operate. Absolutely. Fuel cells are galvanic cells. They occur in spontaneous reaction. If those two reactants come together, they will react. So we don't want that to happen. So that's why we have to separate them. So choose basically A. They must be separated. 12. An electrolysis cell contains a dilute solution of potassium chloride and a potassium bromide. Both electrodes are made of graphite. Which of the following options shows the initial observation at the anode and cathode? So this is electrolytic cell. Now they are aqueous, so water will be reacting. We know that there is going to be K plus ions, chlorine ions, and bromine ions. So looking at my graph here, let me rub all these out. So water is here. Here, K plus is here, chlorine's here, and bromine's here. So which one is, so what are we looking at? Which of the following options shows the initial observations at the anode and cathode? Easy. So the anode is going to be basically what's going to react in. Remember, it's the one on the left and it's the highest one. Which one? Which is this. So it will actually be creating hydrogen gas and OH minus ions. But basically, you got hydrogen gas. So cathode will be basically colorless bubbles. Remember, hydrogen gas is colorless. So these are wrong. What about the anode? Now, if you're looking down at the strong, finding the one that's the strongest reducing agent, so downwards, it's bromine. And bromine's going to basically form bromide 2. And remember, bromide 2 is when you form that, it's actually brown color. It has this brown color. So it's D. Now, luckily, you guys, in the new, this is the old, of course, data booklet that I'm using, but in the new data booklet, you do actually have the colors. Like, for example, bromine, if you're going from bromine, ions to bromide 2, so you actually can see the color change, which is crazy. But whereas this one, we don't. So, yeah. Let's have a look at the next question. All right. Question 13. A reaction has an activation energy of 50 kilojoules per mole and an enthalpy change of 10 kilojoules per mole. A catalyst is added to the reaction to increase the rate of reaction. Which of the following options would represent the catalyzed reaction? So, potential energy of the reactants we have the maximum potential energy of their energy profile, the potential energy of the product. Easy. Let's have a try at drawing this. So if I draw an energy profile diagram here, we know it's endothermic because the enthalpy change is positive, so meaning that it's going from low to high. Beautiful. Now, if we know that enthalpy change is 10, means the distance from here to here is 10. We also know that enthalpy change is 50, meaning the distance from here, the reactants, to the maximum peak is 50. Now, this is an uncatalyzed reaction. If it actually gets catalyzed, so let's use a different color. Remember, it has the same energy of the reactants, but basically the difference is it has a decrease in terms of your activation energy decreases. Let's have a look at first A. Does A meet all those requirements that we've done? Okay, so the potential energy of the reactants is 10. So we're starting with 10. Let's check that. Meaning that this part from here to here should be 10. Okay, let's check. Next one. The maximum potential energy of the profile should be 60. Wrong. Wrong. We're looking at the red graph. Remember the catalyzed reaction. Now, it's 60 for actually the uncatalyzed reaction, but it's, yeah, so take that, A is wrong. And B is wrong because it's basically these two are the same. So it has to be C and D. Now, okay, C basically has different reactant, which is 20. So let's change this to 20. So 20. So the maximum potential energy of the energy profile is 40. Let's check. Okay, it is less than basically 60. Of course, yep, that works. And also that works, 50. And the potential energy of the product is what? Remember, the potential energy doesn't change. It's basically the distance from here to here, which is 10 plus 20, which is 30. So it is C. 14. A Max-Boltzmann distribution curve is given below. Luckily, you guys don't have to know this. It's kind of, they took it out of the study design. Which of the following statements about the curve is true? The temperature is constant? Could be, because, of course, the graph is not moving. So remember, different temperatures basically affect the graph. High temperature basically make it like this. Lower temperatures basically make it like this. So it could be true. The gradient of the curve is the reaction rate. Not true. That's not absolutely true. The peak of the curve is the maximum energy. No, it's actually the average. It's the most molecules, like this tells us the molecules, the number of molecules. It's basically the number of molecules that have the average kinetic energy. What the average kinetic energy. So not the maximum. The area under the curve is the activation energy. Wrong. The area under the graph is the number of particles. So A. 15. Consider the following structures in addition to those on page 8 of the following data book. Which two monosaccharides combine to make maltose? So this one here. Well, having a look at it, the most easiest way to look is look at the bonding down here. You can see that this one's downwards and this one also downwards, meaning that it's like this one, if it bonded with galactose, it would be like this. Can you see how this bonds up? Whereas this would be down, it'll look like this then. It'll be like a glacidic like that. So, but because they're it means that basically these sides always, both of them had basically like, this one had a downwards, whereas the other one that bonded with it also had a downwards. And so when they basically bounded, they formed something like a V shape basically. So which one has that? Let's have a look at A. B, fructose. Absolutely not fructose. None of them look like fructose. Let's have a look at fructose. Let's look at fructose here. Look at the fructose. Does this look like fructose, any of these here? It has an O here, look. Looks like the shape. Whereas these ones don't look like, they look like hexagons. So absolutely rubbish. So not even anything will be fructose, take that out. That one. Next one, galactose. Galactose. I'm looking at galactose. Not true, because you've got, like, if this was galactose, this one would be up. Because remember, this one here is up. Well, let's say this one was galactose. This would be up, so meaning that it would form something like, basically like this. Oxygen here, and it would, this one would be kind of on top of it. So nah, absolutely not. So it has to be D. Alpha glucose and alpha glucose? Well, let's check. So we know if they're both alpha glucose, let's check. So this one's at the bottom. Okay, this one's at the bottom too, because, it's pushed down at the bottom. Also, this is at the bottom. So this one's also bottom, and that's why they create this nice O. Yes, it looks like D is your right answer. Beautiful. 16. Consider the following statements. Hydrogen bonds exist between aspartame molecules. Let's check. Just check these straight away using our data book. So we're talking about aspartame. So aspartame is here. All right. So first question, hydrogen bonds exist between aspartame molecules? Yes, they do, actually. We have a lot of oxygens, nitrogens, oxygen, nitrogen. We have a lot of, we can actually form those hydrogen bonding. That's good. A glycosidic linkage exists between within a molecule of aspartame. Remember, glycosidic linkage is like an O, like that. So let's have a look. Not true. Like this one here, this part here is an actual ester group. This one here is you've got like a amide group here. So that's not true. And this one here is a carboxylic acid. Not true. That's wrong. The energy content per gram of aspartame is similar to what? Sucrose. Yes, actually. What the good thing about aspartame is they actually have the same energy content. But you gotta remember, aspartame is like 200 times sweeter. So basically, if you're, those no sugar drinks like Pepsi and stuff, basically they have aspartame in such small amounts because remember, they're 200 times sweeter than sugar. So they kind of, so if you're only using a little bit of aspartame, it means you're using a little energy. You only have a little energy content, which is actually kind of good. And that's why. So this is great. So which of the following statements are both got correct? So it's only 1 and 3. So choose C. Nice. Last question. In the electrolysis of 6 mole of sodium chloride solution, NaCl aqueous, the amount of charge required to form 1 mole of NaOH aqueous is what? Let's have a look at this part here first. So we want OH, NaOH. Okay, so let's look at this part here first. We have Na plus chlorine ions, and it's with water because it's aqueous, so considering water too. So let's look at that. And what's that going to form? Going back to my... There it is. Rubbing these out. Let's cut these out. Okay. So we have, of course, water. That's water. That's water. NaCl, so Na here, Cl here. So remember the strongest one that basically gets on the left, and it's the highest one on the left, which is your strongest reducing one, your oxidizing agent, which is going to form this here. So 2H2O plus 2 electrons goes to hydrogen plus 2OH minus. And whereas the strongest reducing agent is your 2H2O, and that will form oxygen gas and stuff. But remember, this here molecule is actually OH. So this molecule is very useful because it has an actual OH, whereas the other one has H pluses, so very useful. So we only need this for calculation. So let's get rid of that. We're going to be needing this one for our work. Now, they told us that we want to find the amount of charge required to form 1 mole of NaOH. Now, if we want to form 1 mole of NaOH, it means this is the same mole of OH here, NaOH, so OH minus, which is basically 1 mole. Using ratios, the number of moles of OH is going to be equal to the number of moles of electrons. As you can see, the ratios are the same, 2 to 2. So electrons. That means basically your mole of electrons are actually 1. So, using your formula to calculate charge, which is Q, it's actually number of moles of electrons times your Faraday's constant, which is 96500, which gives you 1 times 96500, which gives you 96500, charge, which is coulombs. Which one looks like closest? It looks like B is your answer. Beautiful. And that is it. I hope you guys enjoyed the video and learned something from this video. I hope it helped you understand some of the concepts here. Please make sure to like and subscribe for more future videos like this, and take care of yourselves. Bye-bye.